So our last video in the integration by substitution is doing a few examples for definite integrals. So with the definite integral, let's just remember just a basic one without substitution first. So say we had 0 to 1 of x squared plus 2x. We first would integrate. We don't need the plus c because we're going to plug these numbers in, and we talked about this in class, but it would just cancel out. And then you plug the 1 in, and then you subtract with the 0 plugged in. So we're going to plug the 1 in, and then, so whatever's on top, plug that in, and then subtract. The 2's cancel, and that would be 0 and 0. So 1/3 plus 1. And that would be your answer. Now going back to the start, right here, these are x values, right? So these are the x values that we plug in later. Now what's going to happen is if we had a definite integral, we're not going to have x's in here anymore. We're going to have u's. And so we need to go back and change these as well as changing the x values. So let me show you an example. Okay, so here we've got a bracket to a power. We're going to call u the inside of the bracket. Take the derivative. And so this will be u. That will be all we need to get rid of. So du over 5 is dx. So there it is. And so that takes care of this and that. But these are x values. So we have to change that. So those are our limits of integration. So when our lower bound, so 1, when x is 1, you plug it in here to find what u would be. U would be 5 times 1 minus 1. And then when x is 2, plug that into u. So u would be 5 times 2 minus 1, which is 9. And then we would rewrite this. The 1 is now 4, and the 2 is now 9, the square root of u, and this is du over 5. And then we would integrate, add 1 to the power, divide by the same number. So this would be 1/2, flip that over, 2 over 3, u to the 3 over 2. Okay, so we have 1/3 u to the 3 over 2. So we just plug these numbers in, so we'll have 1/3 9 to the 3 over 2 minus 1/3 4 to the 3 over 2. 3 over 2, that is the square root of 9 cubed, and this one is the square root of 4 cubed. And that would be your answer. So you notice that we change those limits and we never replace the x back into the integral. So we don't have to go back to x. We just use the values of u, plug it in, and we get the number. Okay, so there's one more step here, but we don't put the x back in here. Okay, so we're just going to do a couple examples of this. And that will give you a few more examples of substitution, sort of a mixed varieties. Okay, so this one we could do not using substitution, because that's linear, so we could just say this is 6. The integral of cos is positive sine 3x divided by 3 from 0 to pi over 2. So we didn't need to change these because I didn't change that. Now, if you did choose to use a substitution, you would change them. What I wanted to show you with this example is plugging in that pi over 6. This is 3 times pi over 6. So sine 3 times pi over 6 is pi over 2. So sine of pi over 2 is 1, and sine of 0 is 0. So your answer would be 2. All right, now let's do a trig example that we do use substitution for. Okay, so this is a bracket to a power, and in the bracket we have cos x, and that's all cubed. So we could let u equal cos x. The derivative of cos is negative sine. And we do have a sine and a dx, so we rearrange this. Du over negative 1 equals sine x dx. This is going to be u, and then we need to change our limits of integration. So when x equals pi over 4, then u would be cos, because u is cos, of pi over 4. It's root 2 over 2. And when x is pi over 3, u will be cos of pi over 3, which is 1/2. So pi over 4 was root 2 over 2. Pi over 3, that was on top, is 1/2. We're dropping off the sine and the dx, so deal with the u first, u cubed. Drop these off, and in their place, du over negative 1. I'll just move the negative sign out front. Okay, so we integrate minus u to the 4 over 4. And we don't go back to the x's, we just plug these numbers in. Let me write it like this. U to the 4. Just so that it's easier to plug in. So then we're plugging in the top number first, so 1/2 to the 4 minus a minus 1/4, so it'll become a plus, root 2 over 2 to the 4. When you do the 4th power, you would do 1 to the 4th, which is just 1, and 2 to the 4th, which is 16. Root 2 to the 4th is 2 to the 4 over 2, which is 2 squared, or 4, and 2 to the 4th power is 16. We could cancel these, but I just noticed that these have a common denominator already. 16 times 4, and this would be minus 1 plus 4. And 4 times 16 is what? 3264? And there would be your answer. Okay. I'm just anticipating I might need my calculator. I don't see it around. I'll grab it if I need it. Okay, so that would be your answer. And so we use u's. We change these using your value of u. So we change them, and then you put them back on in the right order. So that's really important, because sometimes these numbers will be, it won't be the smallest and the largest number anymore. You see, 2 over root 2 is bigger than 1 over root 2, so they're in the opposite order now. And that's fine. You can just leave them like that, but you have to make sure you plug them in the right order. So it's the top number minus the bottom number. Okay, 3, 0 to 1, x squared e to the x cubed plus 1. Okay, so this is exponential with the x not being an x as the exponent, so we'll call that u. The derivative of that is 3x squared. We do have an x squared here, so we want to save the x squared and the dx. Oh, and change our limits. So these were x values. So when x is 0, then u will be 0 cubed plus 1. And when x is 1, u will be 1 cubed plus 1. So 0 changed to 1, and the 1 changed to 2. Deal with your u first, so e to the u. These drop off, and in their place, du over 3. So 1/3 integral of e to the u is e to the u. And we don't need to go back to x's, we just plug that in, and that would be your answer. You just leave it like that. You could say this is e squared minus e, factor out that, but this is fine like that. Oh, I didn't have a fourth one, but let's do one more. Oh yes, I do. Here's my fourth one. I thought I had 4. 0 to 1 arctan x over 1 plus x squared. Okay, so with arctan, as long as there's a divided by 1 plus x squared, then we can use substitution to do this. And I did say before with logs and inverse trig that there are only 2 ways to do these. They're either by substitution because they have the derivative in it, or they're by parts, which we'll do that type later, but those are the only 2 options, so you always try substitution first. So arctan x, the derivative, 1 over 1 plus x squared, which we want. And then we change our limits of integration. These are x values. So x equals 0, u will be arctan of 0. And so that's saying tan of what is equal to 0, and that would be tan of 0. So that stays as 0. X is 1. So we say tan of what is equal to 1, and that would be pi over 4. Okay, so you do need to know these values because you won't be able to use a calculator. The only part of the course we're using the calculator for is that first part with the Riemann sums. Okay, so we write this out. 0 stayed 0, and this was now pi over 4. Arctan is u, and this stuff was du, just du. So u squared over 2. Just going to move the 1/2 out front to make this easier to plug in. So 1/2 pi over 4 squared minus 1/2 times 0 squared, pi over 2. 2 times 4 squared is, that's 16, so 2 times 16, 32. That would be your answer. Okay, so that's a few examples, And then I've added another set of questions that does the rationalizing substitution. I think I might show you one rationalizing substitution here. So the rationalizing substitution, and then these definite integrals, which will also be on the test. Okay, I don't think we did one like this. We can make this into a definite integral as well if we wanted to, something like that. Okay, so these rationalizing substitutions, the way that they work, you're going to call u x plus 1, and will this work? Wait now. Okay, well if it doesn't work, we'll just stop and I'll make a new one, but I'll show you, because this is what you would do anyway when you're integrating. So 1, and then here, what that will do when we plug it in, we'll have square root of u, and then dx is du. But we'll still have this x cubed here. So can we use this to get rid of x, or to get the x cubed? Yes, it's not going to be easy. I should have made a little easier one here. This isn't quite what I was thinking I was doing. But if we solve for x, so u minus 1 equals x, but now we need x cubed. So u minus 1 cubed equals x cubed. This isn't going to be necessarily nicer, because what we need to do now is cube this. So u minus 1 times u minus 1 times u minus 1. So this would be u squared minus 2u plus 1. That's these first two, times u minus 1. Okay, and if we put that in, we'll finish it because I did this question. I don't really know another way that you could solve this anyway, so it would really be done this way. And now let's change our limits of integration, and then we'll integrate this. So we started with x equals 0, and we want u to be, u is x plus 1, from right here. So 0 plus 1. And then we want x to be 3, so u will be 3 plus 1. So we'll put these on 1 to 4. All right, now how do you solve this? Well, we would write this as a half power. And then multiply it through. So when you multiply it through, you add the exponents. So we'll have u cubed times u to the half. So this is 6 over 2 plus 1 over 2. I made that as a fraction over 2. So that will be 7 over 2. The next one, u will have u squared times u to the half. 4 over 2 plus 1 half is 5 over 2. And then we'll have a u times u to the half. That's 2 over 2 plus 1 over 2. And that should be good. Okay, so this times this, we did it off to the side, was u to the 7 over 2. Here will be minus 3, u squared times u to the half. So u to the 5 over 2. This third one, plus 3, u, add the exponents, so 3. And then the last one, minus u to the half. That's 7. Okay, we're going to have a bunch of square roots to do here. So add 1 to the power. So when you add 1, we're going to add 2. So 9 over 2 divided by 9 over 2. Add 2, so 7 over 2 divided by 7 over 2. Add 2. And add 2. So this will be 2 over 9 square root of u to the 9th power minus, flip that over, 2 times 3 is 6 over 7 square root of u to the 7. Flip that over, 6 over 5, 2 times 3 is 6 square root of u to the 5 minus 2 over 3 square root of u to the 3. And you didn't need to write them as square roots, but I can see that they'll work out. So square root of 4 I'm plugging the 4 into everything because that's the top number. And then plug the 1 in. Subtract. Okay, 2 over 9 times 2 to the 9. I'm not going to work this all out. I think this is fine because I'm not going to make these into a common denominator. Times 2 to the 5 is 2 cubed minus 2 over 9 minus 6 over 7 minus, plus 6 over 5 plus 2 over 3. These are all going to be 1. Square root of 1 is 1, and 1 to the 9th. I just applied that minus. And you could work this out, but that would be an acceptable answer for that question. Now, what I was thinking of was if we did something like this. Let's try it. U is equal to x squared plus 1 du is 2x dx. Okay, so now if we go over here, if you notice, we can split this up into an x and an x squared. So x squared plus 1 is here. That's going to be u. And then with our derivative, we have both an x and a dx. That takes care of these two. And all that's left is an x squared, which we can use u equals x squared plus 1 to solve for. So u minus 1 equals x squared. So if we plug those in, so the x and the dx are going to drop off. Here, x squared, I'm going to call u minus 1, square root of u, and these drop off, and we get du over 2. This one, it doesn't involve as much expanding. We would just multiply this through. U to the 5 over 2 divided by 5 over 2. 3 over 2 divided by 3 over 2. And you could put that 2 in. Actually, that works nice because the 2's will cancel. So if we multiply this through, we'll get 1/5 root u to the 5 minus 1/3 root u cubed plus c. And if I had put this as a definite, integral, then we would plug in the u's here. But I didn't, so we do need to go back to the x's. And x was x squared plus 1. Okay, so that was a little bit longer, but it has all the possibilities in it. And so we have a test on May 22nd. And remember, it covers everything from the start until this lecture. You can practice the questions from the lectures. You can practice the questions from the homework. And it goes from problem set 1 to problem set 4B. There's 2 problem sets 4. There's the first 4, and then I added the second one that is dealing with these things. So you would practice those. And that test is worth 10%. Okay, there's no class on May 20th, I believe. May 20th is a holiday. I didn't realize that before. And so no class May 20th, so our test is on May 22nd. I'm in my office on May 21st all day. So from 8:30 until 3 in Tilly 422A. Or the Math Learning Center is open on Tuesday from 5 to 9. Okay, and just send me an email if you have any questions. Oh, there, sorry about that. So no class May 20th, it's a holiday. So May 21st, I will be in my office. This is office hours. And, or you can email me, Caroline@unb.ca. I won't have access to my cell phone data, so I won't be able to get text, but I will get my email in the evenings. And the Math Learning Center is open Tuesday, or it's open all week. Monday to Thursday are the regular hours, 5 to 9, so you can actually go during our class times while I'm away. And but right before the test, it won't be open Monday because Monday's a holiday. So on Tuesday, May 21st, it would be open 5 to 9, the day before our test.